All right, you guys, here we are. I'm in the middle of page 5. I'm just picking up where we left off in class. Let's see, we just finished that example about cars sold and the probability of number of cars sold on a randomly chosen Friday at a car dealership. Remember, we had talked about what happens when the dealership's manager gets a bonus and what he does what happens to his amount of money he brings home when he spends $75 on coffee and donuts, whatever. So we're in the middle of page 5. Now we're going to talk about this problem called scaling a test. And so we actually do this in stats class. A lot of times we give you like a multiple choice test and it's out of like 20 questions, and then we multiply it by something and we curve it by adding some points to everybody's score, and then we take it out of 100 in the grade book. So this is really common. We have a random variable x, stands for the raw score on a test, and we've got a mean and a standard deviation of the raw score. Let's say it's out of 20 or something like that. So average score 17.2. Professor decides to scale the scores by multiplying by 4 and adding 10. So define the variable y. So keep in mind, x is the raw score and they want y to be the scaled score. So pay close attention to that because the letters that you use are really important. You have to be very diligent and pay close attention to the letters that you're using. So find the mean and the standard deviation of y. So keep in mind we are multiplying all the raw scores by 4 and we are adding 10 to all the raw scores. So I'm going to define my mean of y as 4 times the mean of x plus 10. So whatever my average is, I'm multiplying it by 4 and I'm adding 10. So whatever you do to the scale, to scale all the scores, that affects your average the same exact way. So I'm going to plug in the 17.2. It was right here. It's the average raw score plus 10. And that's going to give me a mu of y, which is 78.8. No big deal, but then just keep in mind, when we're talking standard deviation, yes, if you multiply all of the values, they do get more spread out. But if you add 10 points, if you curve everyone's score by just adding, everybody gets 10 points, that just shifts all of your values up. Or if you subtract, it shifts all of your values down. It does not affect the spread. So just keep in mind that the sigma of y is just going to be the 4 times the sigma of x. You ignore the 10. Adding 10 to everybody's score does not impact the spread. So keep that in mind. So we've got 4 times 3.8. That gives me my mu, or my sigma of y as 15.2. Cool. Make a little note about how adding and subtracting does not affect spread. Add, subtract, doesn't affect spread. Cool. What's the probability a randomly selected student has a scaled test score of at least 90? So up here in the wording of the question, I kind of skipped over this because we're going to get to it in letter B. It does say it's normally distributed. As you know, whenever you see that in your wording of your question, that's really, really important. That gives you a huge clue. You're going to probably using some sort of a z-score, table A, etc. So I'm going to rewrite this. I'm going to say the probability that y is at least 90. Remember, the y is the scaled score, the x is the raw score. Convert this to a z-score because it tells me it's normally distributed. So I'm going to convert to a z. And when I convert to a z, my letter changes from a y to a z. This represents z-score. So I'm going to take my 90 minus 78.8, my x value minus the mean divided by the standard deviation. Those are the same values that we got up here, the mean of the scaled score and the standard deviation of the scaled score. That gives me a z-score of, let's see, what was it? 0.736 or 0.737. Okay, so now what do I do with that? So just keep in mind, what does a z-score tell us? Is that my percentage? Is it like 74%? We tend to get really confused on the difference between a z-score and the percentile. So remember, we've got our mean here, which is 78.8. We've got 3 standard deviations to the right, 3 standard deviations to the left. That 90, it tells me that it is almost 1 standard deviation to the right of the average. And we could label these tick marks too, but that means I'm going to draw my line here at 90 and I'm shading to the right. 90 goes right there. It is a little bit less than 1 standard deviation above average. That's what that z-score tells me. So what's the shaded area? Let's go back into table A really quick. Remember, table A has all those z-scores. The first page is negative z-scores and the second page is positive z-scores. And I've kind of written on this a little bit, but we're looking up. The z-score was 0.737 or 0.74. So 0.74 tells me here is my shaded area, 0.7704. So going back to my picture, this is why I always love to have a picture on everything. That 0.7704 is not my shaded area. Remember, it's always area to the left in that table. So you have to subtract from 1, and we get what? 0.2296. About 22%, 23% of randomly selected student has a probability of almost 23% of having a score of at least 90. Okay, so let's go on to the next question. Remember we talked about this El Dorado Community College situation when I ranted about the $200 fee that DePaul charged me every single quarter when I was a student there. So remember we had already kind of started talking about this, and we came up with some values on the previous page where we have the mean cost per semester, which is tuition plus that $100 fee. That was the $832.50. And the standard deviation was 103. We actually calculated 102.81, but I just rounded it to 103. So these are the two values that we came up with earlier when we started having that conversation about tuition plus fees. And so now don't forget, my friends, that when you go to college, you have to pay tuition. You also have to pay room and board and some sort of a meal plan and all these fees, but you also need textbooks. So we have a new random variable. It's going to be B, the amount spent on books in the fall semester for a randomly selected full-time student. So on average, they're spending $153 with a standard deviation of 32. And so remember that C was the overall cost, which was tuition and fees. That was the number that we already calculated, 832. So find the mean and standard deviation for tuition, fees, and now books. So what I'm going to do is I'm going to have my mu of C plus B. When you add means together, you just straight up add them. Nothing fancy about it. We have our total cost on average plus the textbooks on average, which gives us an average cost of about $985.50. You just add your mu from your cost, which is this number, and the mu from the books. Add them up. No big deal. Okay, but here's the thing. We're not allowed to add standard deviations together. So we have to do something a little bit fancy. You guys should have read about this, and you should have something in your reading guide. And I have another confession. I'm full of stories these last couple days, but I took statistics when I was at DePaul. And I was really excited because I was taking statistics at DePaul, and I already knew I was going to be teaching it at FREM the following year for the first time, and I was super excited and motivated to do really well at stats. I missed one question on the final, and it is because I added standard deviations together. So you should have written in your reading guide that we aren't actually allowed to add standard deviations. What we have to do is we come up with the sigma squared first by adding the two variances together. That means I'm going to have to take this number and square them and add them together. Let me take you back to Algebra 2 for a second. Do you guys remember the fact that you're not allowed to add square root of 2 and square root of 3 together? Does that equal square root of 5? No. Remember, they have to be like terms in order to add them together? These are not. That is how I remember, and I did not do a good job remembering when I was at DePaul. But that's how I kind of think about the reason why we're not allowed to add standard deviations. Mathematically, you're not allowed to add them. We have to add variances together, and then we take the square root to come up with the sum standard deviation. So here's what that looks like. We take our 103 squared and our 32 squared. Those are just the standard deviations of the total cost, which we calculated on the previous page, and the standard deviation squared for this amount of money spent on books. Come up with that number. And then what we have to do is we have to square root it. And that gives us our grand total of $107.86. So big, important thing, asterisk, star it, do something, make yourself a note. I will never forget. The shame still haunts me. I added standard deviations on my final exam at DePaul to get my master's degree in math. And you're not allowed to do that, guys. You got to add the variances together. As you can see, this next page is my video. So hopefully you've watched that. You should have watched it by now. But that is this page. So I'm going to go right into this last example. Okay, so I am going to go right into this problem in the middle of the page first, and then I'm going to do the top and the bottom real quick. I want to start by talking about speed dating. No, my friends, I do not have a story about speed dating. As you know, I met MB when we were in chemistry class sophomore year in high school, and we never looked back after that. So I fortunately have not had to have a speed dating experience, so there is no Mrs. J annoying story to go with this problem. But supposedly we have normally distributed distributions for the heights of males and the heights of females. We have two different means, two different standard deviations. Most of the time females are shorter than males. That's common knowledge. It's not always the case, but sometimes it is. So what's the probability a randomly selected male is shorter than his female partner? So if I were to go speed dating, what are the chances that I sit down across from somebody that is shorter than me? So keep in mind, when you're comparing heights for a guy and a girl, you're probably subtracting, am I right? So we're going to take our two means, the mean for the males minus the females. We're just going to subtract them because we're trying to find the difference. The average height of males, the average height of females, you subtract them, and that tells you how much taller, on average, the male is than the female. Remember, for standard deviations, though, we cannot subtract standard deviations. We have to, in fact, add variances. But wait, aren't we doing a subtraction problem? So no. What I want you to think about here for just a second is that we have a distribution on some sort of a number line. For example, we've got all the values for heights over here, and so the female mean is like 65 inches and the male mean is 70 inches. Something like this. This is my illustration to help you understand why we are going to add variances and not subtract variances. This is in your reading guide and also in the textbook as well. But we've got a female distribution that looks something like this with an average at 65. And we've got a male distribution that looks something like this with a distribution of 70. And so if you think about this, you guys, conceptually, when you combine these two distributions and you don't separate males and females, you just combine them into one giant group of speed daters, what we have here is we essentially have the shortest female hanging out way out here, and we have the tallest male way out here. And when we combine this population with this population, can you see how our shortest female is still going to be right here on the number line, and our tallest male is still going to be over here on the number line? So we're going to actually be a little bit more spread out than initially the two populations were separately. So I know that's kind of a difficult concept to kind of wrap your heads around, but I encourage you to go back into the book and do a little bit more reading about that. Even though we are subtracting males minus females here, we are still adding variances together. Important, very, very important note, we still add variances. So this is how we do that. We get 3.5 squared plus 3 squared. Those are the two standard deviations we were given up here in the problem. We are adding them together after we square them and then take the square root. So finally, what I have here is the distribution of the difference for males and females with 5 right in the middle, and my standard deviation is almost 5 units. In this case, what are we doing? Inches. And I want to know what the probability is that a randomly selected male is shorter than the female partner. So what does that mean? That means when you subtract them, what is the difference? If the male is shorter and you do male minus female, that means you should get a negative number, right? So I'm going to draw my line at 0 and shade to the left. I believe that is what represents a male being shorter than the female. So here's what that looks like. I want you to keep in mind that you could also subtract female minus male. You would be answering the same question and doing the same math and coming up with the shaded area if you like reversed all of these and did female minus male. That's okay if you wanted to do that. So here we have, I need to figure out the probability that the male minus the female is less than or equal to 0. So drawing my line at 0 and shading this direction, that gives me a difference of a negative amount, which means the female is taller than the male. So again, we convert it to a z-score. I do the x value, which is 0, subtract the mean, and divide by the standard deviation. It gives me this z-score. So again, remember, you're looking up this z-score on table A. You're going to negative 1.08. Yes, there are calculator ways that you can do this, but let's just stick with the table for right now. We're going to be a little bit rounded. And when you come up with that percentile, that 4-digit number that you're looking at that corresponds with negative 1.08 on table A, that gives you this shaded area because it is to the left. If you wanted to know this shaded area, you would subtract that from 1. So here's what you get. And there's our interpretation. 13.9% chance that a female sits down across from a male that is shorter than her.